So, next we will look at properties of the outer measure. So, recall that we just defined the outer measure on subsets of Rn. For each subset of Rn we have a positive number associated to it. It may be 0 or a positive number, or it could be infinity also. And this outer measure is supposed to give us a countably additive measure when we restrict it to an appropriate sigma algebra, that will come later. Before that, so towards to move towards such a goal, we look at basic properties of the outer measure we just defined. So, let us recall that. So, properties of outer measure. Okay. So, we will keep this in the side. So, m star of E was defined to be the infimum of certain quantities. This is summation mod qj, j equal to 1 to infinity, qj were closed cubes and it was a cover of E. So, you cover E with closed cubes, form this quantity and take the infimum. So, properties of outer measure. The first one, this is monotonicity, we just saw this. So, I will be brief here. Monotonicity, if A is contained in B, then m star of A is less than or equal to m star of B. Okay. So, this immediately, so this we saw earlier. So, this immediately implies that m star of the whole space Rn is infinity, right, because you can take any take big cubes, right, take big cubes Q contained in Rn and that will become bigger and bigger, right, because if Q is contained in Rn, m star of Q is less than or equal to. So, m star of Q is less than or equal to m star of Rn, but m star of Q is simply the volume of Q and the volume of Q can be made as big as you want. Okay. So, that is easy. Okay. Second one, second property, this is called subadditivity. Subadditivity, again a very natural property to have when you look at measures and so on. So, if E is equal to union Ej, j equal to 1 to infinity, okay, then m star of E is less than or equal to summation j equal to 1 to infinity m star of Ej. This is called subadditivity, right. The volume of E, so imagine these are all cubes, then volume of E will be less than or equal to sum of volumes of Ej's, right, because Ej's may overlap. So, that is what is reflected here and it is true for all sets. So, that is the important part. So, let's prove this. Okay. So, we start with assuming that m star of Ej is finite for every Ej. Okay. Otherwise, the right hand side will have an infinity and then this, otherwise this is trivial, right, otherwise this is trivial because the right hand side will have an infinity term and then we have the inequality clearly. Okay. Now, m star of Ej is finite. So, there exists a covering. So, there exists a covering. So, this is what I had mentioned as soon as the definition of m star was introduced, because it is the infimum. For every epsilon you have a covering with certain property. So, there is a covering of Ej. Okay. So, Ej contained in Q, well, notation has to be clear, Q Kj, okay, union k equal to 1 to infinity. What are Q Kj's? Q Kj are, these are closed cubes, okay. So, for each j I have Q Kj's. And and summation k equal to 1 to infinity modulus of q kj is less than or equal to m star of Ej plus epsilon by 2 to the j, right. So, of course, we always start with an epsilon. So, maybe I should have said that first. So, let us put this here, fix epsilon positive. So, there exists a covering of Ej such that this happens, right. This is just the property of infimum, right. The epsilon by 2 to the j is a positive number. So, I will have a covering with this property. So, keep that property, keep that inequality in mind, because that is something which we will use. So, QKJs cover EJ. So, and EJs cover E. So, if I put together, I will get, so now we have E contained in union QKJ, right, k equal to 1 to infinity, j equal to 1 to infinity, because of this property, right, and E is simply the union of Ej. Okay. So, hence m star of E, remember m star of E is the infimum, right, m star of E is the infimum, of certain quantities, and this is a cover, right, this is a cover of E by closed cubes. So, if I sum up mod QKJs, that would be a number in the set where we take the infimum of. So, m star of E will be less than or equal to summation QKJ, k equal to 1 to infinity, j equal to 1 to infinity. But this is less than or equal to, because I know, okay, so let me write one more time so that this is clear. So, this is nothing but summation j equal to 1 to infinity, summation k equal to 1 to infinity mod QKJ. But this quantity is less than or equal to, so we chose those covers with some property, right. So, this is less than to j equal to 1 to infinity m star of Ej plus epsilon by 2 to the j, right. So, that is how, remember, this is how we chose it, right, 1. So, this is by 1, which is simply summation j equal to 1 to infinity m star of Ej plus epsilon. Okay. So, we have m star of E less than or equal to m star of summation of m star of Ej plus epsilon for every epsilon positive, right. So, I can let epsilon go to 0. So, to get m star of E less than or equal to summation j equal to 1 to infinity m star of Ej, which is the subadditivity property, right. So, if E is the union of countably many sets, we will have the subadditivity property. So, this argument is something we will use again and again. Okay. So, let me give it a name. So, this argument, so we will call it the epsilon by 2 to the j argument, epsilon by 2 to the j argument will be used again and again. So, this is something you should understand very clearly. So, we have two properties, monotonicity and we have subadditivity. Next one, another important property, third property, this is called outer regularity. Regularity. Okay. Well, what does that say? If okay, if E is a subset of Rn, then m star of E is equal to infimum of, well, it is not the definition, it is going to be m star of O. What is O? O is an open set. A is contained in O open set. Open set in Rn. So, you look at all the open sets containing E, look at m star of all those open sets, take the infimum, that is what m star of E is. So, remember this is not very surprising, but at the same time it is an extremely important property. Well, how will you prove this? Okay. So, as usual we want to prove two things are equal. So, we use the inequalities. So, we will show that LHS is less than or equal to RHS and RHS is less than to. Okay. So, we will show that LHS is less than or equal to RHS and vice versa and the other way. Okay. So, then both of them will be equal. So, as usual one of the inequalities will be easy. So, since E is contained in O, subadditivity tells monotonicity will tell me, monotonicity implies that m star of E is contained in m star of O open set, right. But this is true for every open set containing E. So, I can take infimum on the right hand side. So, take infimum on the right hand side to get m star of E is less than or equal to infimum of m star of O such that E is contained in O and O open, right. This is what we want. So, we have one way inequality, we want to prove the other way. Okay. So, to prove the other way inequality, choose. So, you will see the epsilon by 2 to the j argument coming again and again. So, let's start with fixing epsilon etc., right. Okay. So, fix epsilon positive. Okay. Choose closed cubes, Qj such that E is contained in union Qj, j equal to 1 to infinity, of course that is possible, and summation mod Qj j equal to 1 to infinity is less than or equal to m star of E plus epsilon. This is possible, right. This is simply the property of infimum. So, that is the first thing I mentioned after defining the outer measure, property of infimum. So, given epsilon I can get a cover with this property satisfied. Okay. Well, what do we do with these closed cubes? So, for each Qj, choose an open cube Sj such that Qj is contained in Sj. Well, that is easy, but we have the epsilon estimate there. So, we need to do appropriate, we need to choose appropriate Sj such that the volume of Sj is very close to the volume of Qj. So, mod Qj plus epsilon by 2 to the j. So, remember epsilon by 2 to the j is a positive number. So, all I have to do is to slightly enlarge Qj, right. If this is my Qj, I choose my Sj very close to it, right. So, this is Qj and this would be Sj, right. Only thing is this inequality should be true. Okay. So, you enlarge Qj slightly, okay, this is possible. But now these are open cubes, so I have an open set, right. So, let O be equal to union Sj, j equal to 1 to infinity. This is an open set because the union of open cubes, and so it is an open set, right. And the set E is contained in, well, I know it is contained in union Qj, j equal to 1 to infinity, but surely contained in union Sj now, j equal to 1 to infinity, which is my open set O. So, what I have done is getting an open set O which is slightly bigger than the union Qj. So, O is the union of things, union of Sj, right. So, m star of O will be less than or equal to summation j equal to 1 to infinity m star of Sj. This is by subadditivity, okay, by subadditivity, okay, which, so we have m star of O less than or equal to summation j equal to 1 to infinity m star of Sj, which is equal to summation j equal to 1 to infinity mod Sj, because Sj is a open cube. So, m star of Sj will be the volume of Sj, which is less than or equal to, because the way Sj's are chosen, we have j equal to 1 to infinity mod Qj plus epsilon by 2 to the j, which is less than or equal to summation j equal to 1 to infinity mod Qj, which is less than or equal to m star of E plus epsilon. So, this portion is less than or equal to m star of E plus epsilon, and there is another epsilon, right. So, this is nothing but m star of E plus 2 epsilon. The 2 epsilon does not matter because epsilon is arbitrarily small, right. So, what we have done is, for every epsilon positive there exists O open set, right, such that E is contained in O and m star of O is less than or equal to m star of E plus 2 epsilon. This is true for every open set, for every epsilon, right. Hence, I can take the infimum on the left hand side and let epsilon go to 0, right. So, infimum of all m star of O where E is contained in O open, this is less than or equal to m star of E, right. So, we have the other way inequality. So, this is one inequality, and the first one we started with, that is the trivial part, this portion, right. So, we have the both way inequalities, and so we have proved outer regularity. Okay. So, we will stop with one more property. So, property 4, this is some kind of additivity, but with some strong conditions. Okay. Suppose E is a union of two things, E1 union E2, okay, E2, two sets, and distance between E1 and E2. So, what is distance between E1 and E2? So, this is the infimum of modulus of x minus y, where x belongs to E1 and y belongs to E2. So, that is the distance between the two sets E1 and E2. Suppose this is greater than 0. So, they are not just disjoint, they are at a distance. So, this could be E1 and E2 could be somewhere here. Okay. There is a distance between them. Okay. This is positive. Then we have additivity for the outer measure. Then m star of E equal to m star of E1 plus m star of E2, right. We want countable additivity. So, this is a much weaker property, that if I have E1 and E2 at a distance, then the outer measure adds up. Okay, so let us prove this. So E1 and E2 are disjoint, but disjoint does not mean that the distance between them is greater than 0. For example, I may have an open interval like 0 1, right. E1 could be, or let us say A1 is open interval 0 1 and B1 could be the singleton one. Okay. Then the distance between A1 and B1 is actually equal to 0 because 1 is in the boundary of A1, right. So distance disjoint does not mean distance is positive, but distance positive would surely imply that they are disjoint. Okay. So first of all, by subadditivity we have m star of E, well m star of E is equal to m star of E1 union E2, right. By subadditivity this is less than or equal to the outer measure of each component, right. We proved it for infinite ones, but it's the same one for finite unions. Okay. So we have one way inequality. So we will prove the other way. We will prove the other way inequality as well. Okay. So let us prove that. So let delta positive be such that the distance between E1 and E2 is greater than delta. Okay. So choose a covering for E. Choose a covering for E. Okay. So E is contained in union Qj, j equal to 1 to infinity, Qj closed cubes, right. Then we sum up Q mod Qj's, then take the infimum to get m star of E. Okay. Such that, so again usually there is an epsilon. So first fix epsilon positive, choose a covering for E such that E is contained in this, and summation mod Qj, j equal to 1 to infinity is less than or equal to m star of E plus epsilon, right. So this we have seen this several times now. This is simply the property of infimum. Okay. So now if possible, so let's perhaps draw a picture so that it is sort of clear. So I have E1 here, I have E2 here, and E is the union of these two, right. So I am covering E with cubes like this, right, and so on. But some cubes may intersect both of them, it can be bigger cubes like this, right. So what you do is subdivide such ones. Okay. So subdivide each Qj if necessary, so that diameter of Qj is less than delta. Okay. Then so what is the point? Recall that E1 and E2 are at a distance delta, right. So I have E1 here, I have E2 here, and the distance between them is delta. So if I take a cube of diameter less than delta, then if it intersects E1 it cannot intersect E2. Okay. So each Qj then will intersect only one of E1 or E2. Okay. Only one of the EJs it can intersect. It cannot intersect both of them because the distance between them is delta. So if the cube intersects both of them, the diameter of the cube will be greater than or equal to delta. But we have subdivided Qj so that it is less than delta. Okay. So let's write J1 to be all those indices j such that Qj intersects E1, and J2 to be all those intersects all those indices k such that qk intersects E2, right. So, J1 and J2 are disjoint. Because if there is a common index, then that particular Qj will have to intersect both E1 and E2, which is not possible. Okay. So, I can write E, well, remember this is E1 union E2 to be such that E1 is contained in union Qj, J in J1, and E2 is contained in union Qj, J in J2, right. Because I put together I will cover E, the ones which intersect E1 will cover E1 and the ones which intersect E2 will cover E2, right. They are disjoint, they are far apart. Okay. So, because of this, hence m star of E1 plus m star of E2 is less than or equal to. So, look at this, this is one covering of E1, right. So, this is one covering of E1. So, apply the definition of m star of E1. What do? You look at summation mod Qj where j belongs to J1 and then take infimum, right. So, m star of E1 will be less than or equal to summation j in J1 mod Qj, right. And similarly, m star of E2 will be less than or equal to summation j in J2 mod Qj. But J1 J2 are disjoint, right. I can put together. So, this is less than or equal to summation j equal to 1 to infinity mod Qj, all the Qj's. But the Qj's were chosen so that they were at an epsilon distance from m star of E. So, this is equal to m star of E plus epsilon, right. Remember that is how the Qj's were chosen. So, we had chosen Qj's to be with this property. So, what did we prove? We proved that m star of E1 plus m star of E2 is less than or equal to m star of E plus epsilon. This is true for every epsilon positive. So, this will imply that m star of E1 plus m star of E2 is less than or equal to m star of E. Okay. So, that is one inequality. The other way was easy because of subadditivity, right. So, by subadditivity we had the other inequality. So, this tells me that they are equal, hence they are equal. So, we will stop with this, hence we have m star of E1 union E2 equal to m star of E1 plus m star of E2. So, remember the strong condition we have, provided the distance between E1 and E2 is greater than delta, right, or positive. So, that is enough, it is positive, that was an extra condition. Okay. So, we will stop with this. So, what we have seen in this lectures is the definition of the outer measure, and it is defined for all subsets of Rn, and we saw some properties, monotonicity, subadditivity and outer regularity, along with additivity property if the sets are disjoint and at a distance greater than 0. That is very weaker than countable additivity. So, in the next lectures we will restrict the outer measure to a sigma algebra called the Lebesgue sigma algebra, and we will prove that it is actually countably additive in that sigma algebra. So, that will complete the construction of the Lebesgue measure on